Let me request the normal people to come. Okay. Anyway, hope you guys had a great winter break. Today we'll be learning about SVMs or support vector machines. This algorithm is pretty important in machine learning, and it often can actually produce results that are better than a lot of other techniques, including more sophisticated ones like deep learning. And so this is a very important concept. So quickly before we start on the lecture today, I quickly want to talk about what we learned in our last class of 2020, which was random forests and decision trees. So can someone? Oh, hold up. I think my Wi-Fi is kind of bad right now. Can everyone hear me? Okay.
Yeah.
Yeah. Okay. Cool. Yeah. So quickly, could someone just raise their hand and tell me what they know about decision trees? Like, give me a quick definition of what a decision tree is, when it's commonly used, and how the random forest algorithm is based on decision trees. Anyone? Okay, I guess I'll call on people if nobody answers. Or I guess I can just re-explain just to make sure. How do you guys want to do it? Anyone just want to answer? Maybe one person can just answer the first part. So, what are decision trees, and sort of when are they good and when are they used?
It's a diagram of different outcomes.
Mm-hmm. Yeah, that's correct. Decision tree is a diagram of different outcomes, and essentially that's like the most simplistic version of a tree, right? It just sort of has this if-else sort of narrative of a tree. So it's like if this condition is true, we choose this outcome, and we sort of split along different nodes based on what sort of questions we can ask that produce the most separation between our different samples in the training set, right? So essentially, we talked about briefly about these different algorithms like information gain and then sort of impurity index that we can calculate. If you aren't sure exactly what I'm talking about, just look at the notebook from last week. That has more information on those specific algorithms. But essentially, random forest is just a bunch of decision trees put together. And the reason why this is a very powerful algorithm is because a single decision tree can usually be very biased, right? Because if you have very different a very different distribution of data in the testing set, in the training set, then what you might end up with is a really badly performing decision tree because it's so badly biased by what it saw in the training data. So to combat that, if you put together a bunch of different decision trees to make a forest of trees, a proverbial forest, then essentially what you'll end up with is something that can combat the bias better and sort of gets an average of the algorithm. So you have a more consistent algorithm and also a better performing algorithm. So that's where random forest can be used. And yeah, that's like the main information from last week that's important to know. So yeah, one other thing I want to mention is that decision trees are often sort of the bread and butter of the intro to machine learning, just because they're super easy to interpret and model, right? Because all these other different machine learning algorithms that we're going to talk about, so starting today and next week and the week after that, are all going to be a lot harder to visualize, and you'll see that through the math involved in computing the sort of equation that fits the data. So yeah, that's what decision trees and random forests are about. And now we'll start on the presentation on support vector machines, or SVMs, today. So anyone have any questions before we start? Nope. Okay, let's get started. Oh, just to make sure, Sam, you're recording, right? Cool. All right. So I took this PowerPoint from this Cornell class because I thought this was a pretty good PowerPoint and it summed up what I wanted to talk about. So yeah, it's from my intro to artificial intelligence class at Cornell. And today we're going to talk about SVMs. So SVM stands for support vector machines. And it's basically, like we talked about, a supervised learning method for classification and regression. And SVMs can either be linear or nonlinear. So they can either represent linear or nonlinear functions. And therefore, that's actually one of the decisions you'll have to make while using an SVM, whether to use a linear SVM or a nonlinear SVM. And this is irrelevant. Irrelevant. Okay, so this is probably the most foundational thing of SVMs, or sort of the idea behind them. So when you have two different outcomes and you have a sort of two different variables modeling them. So let's say we have, I don't know, a measure of height and income. Okay, so say you have height on the x-axis and income on the y-axis, right? Well, essentially what we'll see is, and say that outcome we're looking at is, I don't know, average, or whether or not these people get to retire before the age of 65 or not, right? So red means you're not able to retire before the age of 65, and green means that you are. And on the x-axis, you have height, and the y-axis, you have income, right? So we see a clear trend here. People who are shorter and who make less money aren't able to retire before the age of 65, while people who make a lot more money and are taller are able to, right? So we essentially can fit a sort of line across this plane, and essentially use this.
Andy, are you showing something?
Oh, could you guys not see? Sorry.
I think we can just see the PowerPoint. We can't see the graph.
Huh.
Yeah. Now we can see it.
Okay, I guess I can't use full screen then. Okay, sorry. What were you seeing before then? Before I. Huh, okay, that's weird. But now, if I go between tabs, you can see it, right?
Yeah.
Okay, cool. Cool. Yeah, so I'll kind of re-explain what I was talking about here. So what I'm showing you right here, is, say you have this graph right here, right? And the red represents whether you are able to retire before the age of 65. So the question is whether you're able to retire before the age of 65, and red means that you're not able to, and green means that you are, right? So this is sort of the training data we have. And on the x-axis, we have height, and on the y-axis, we have income. So clearly from the training data, we can tell that people who are shorter and make less money can't usually retire before the age of 65, while people who are taller and make more money are, right? So we essentially can fit this super nice line across the data, which sort of separates it into two different classes. And so on the testing set, if we have a similar distribution of data, we likely will be able to have a very high classification accuracy. So an example of a bad decision boundary. So say we have the same example, but in this case, we fit the data, the decision boundary, such that it's too close to one class over another. So in this case, it'd be an example of a bad decision boundary. And a decision boundary is just a sort of line or equation that separates these classes if it's classification, or fits the data if it's a regression. So generally, I like to focus on classification rather than regression algorithms, just because classifications are easier to visualize and sort of understand. But anyway, so this one's actually a better decision boundary, or a good decision boundary, just because this line is actually kind of more intermediate to the data. So what I mean by that is down here, this line is too close to class 1. And so if you have some people who are like sort of on this edge of having a decent height and having just about a bit above average income, but who actually can't retire before the age of 65, they will be classified incorrectly. And in this case, you can also similarly see why this is an example of a bad decision boundary. And now you might be wondering, right? So there has to be some math involved to kind of calculate this decision boundary or figure out the distance between these sort of points that the boundary has to be placed upon. And you're right, there is a lot of math actually involved here. And I don't want to actually go into all of it just because it's like quite complicated and involves some calculus, some multivariable calculus. So I'm just going to skip that. But for now, I will just sort of give you like the sort of theory behind what makes a good decision boundary. Well, the fundamental principle of a good decision boundary is that the margin between the boundary itself and each of the classes should be as big as possible. So basically try to maximize the margin between these data points, right? So essentially, what's going on here is you do this equation. They're basically setting up sort of these vector equations for the distances at these 2 points or these 2 lines that fit the edges of both the data. And then essentially you're trying to maximize the separation of a line in between these 2 data points. And essentially, when you do all this math, you end up with this sort of maximum margin. That's what it's called, a maximum margin linear classifier, which is essentially your linear SVM. So this is a linear example of what a decision boundary and thus SVM would represent. And this is sort of just for you guys to visualize how the boundary or decision boundary is created. So with nonlinear SVM, which we'll be talking about later, it's not as easy to visualize it, and you sort of have to just go back to your intuitive understanding of what we talked about now for how this complex decision boundaries in like 2 dimensions and 3 dimensions are calculated. Because remember, right now we're only running the SVM with these 2 features, right? We have 2 sort of independent variables and 1 dependent variable. But when you start running data sets that have like 10 to 15 different features or independent variables, you end up having essentially 15 or 14 dimensions to model with just like a single equation. And once you sort of do that, you can't really model it like as you would on like 2D Cartesian grid. So you sort of have to just think back to your intuition of when you only had 2 features. So essentially, you then have to optimize this decision boundary because you sort of first have to pick a good decision boundary, and then you also have to optimize the fit of that decision boundary to the data points to make sure that it has a maximal classification accuracy. So therefore, you sort of have to minimize the equation. Don't worry about the math here again. And basically what you're doing is sort of trying to classify all the points correctly with the highest accuracy. So I'm just going to skip the math for now. Don't worry about it. This is, if you're curious, I'm going to put this PowerPoint up, and you guys can, and if you've taken multivariable calculus, you can sort of try to intuitively get a better understanding of what this minimization is. But if you have taken multi, we talked about Lagrangian multipliers in multi, and we talked about the minimization of functions. So this stuff is covered in multi. Anyway, so yeah, I'm going to skip all of that and then sort of just quickly show that basically after solving that optimization equation, you sort of get more concrete values that are then used to actually plot the equation. So this sort of puts a numerical or objective lens to how we can create a linear SVM. All right, so yeah, so we basically now have to consider the fact that the majority of problems that we're looking at can't be modeled well with linear SVMs. So therefore, we sort of have to use different kernels. So that's what you sort of refer to the kind of function that is sort of sitting behind the SVM. So you would refer to it as the kernel. So if you're running a linear SVM, you're saying you can also say that you're using an SVM with a linear kernel. Or if you're using a nonlinear SVM, you could say you're running an SVM with a polynomial kernel, right? So you can have these different kernels that model different functions, basically. So basically, some smart people in 1992 figured out that you can actually transform data into higher dimensions, which then would allow you to model that data in that higher dimension and eventually get a more fitting sort of equation to fit the training data. So they basically did some complex math and transformed data from this from whatever dimension or lower dimension that it was to the higher dimension. And it basically allows you to take data from the original feature space that you're working in and kind of shift it to a higher or new feature space that allows you to work in a dimension of or work in a space of sufficiently high dimension. So basically what that means is if you start off with this sort of data, right, you can model this data in 2D and you sort of would end up with this sort of circle decision boundary, right? But if you take this data and transform it, right, into this 3D thing, you end up creating a much cleaner decision boundary, right? Because the circle decision boundary seems very, very forced. It seems to fit very well with training data, but likely when you introduce some sort of bias or variation from the testing set into this, you likely won't have such good classification potential with this decision boundary. So you use a nonlinear SVM, transform the data into like a higher dimension, so or higher feature space, so from 2D to 3D in this example, and you end up with a much cleaner decision boundary that can be modeled with this sort of triangular prism. Is essentially what this is, right? Because it fits against the X and Y axis. I'm sorry, the X and Z axis, and you're basically able to have a much cleaner separation of data points. All right, so this essentially leads us to quickly talk about how exactly do you transform this, or it seems like there's going to be a lot of computation involved, right? Especially with large amounts of data, there's going to be this high computation burden to take the data from a lower dimension and move it to a higher dimension. And it's sort of hard to get a good estimate without sort of overrunning the computation that you have. Well, essentially, SVM uses a few tricks. So one is that sort of mathematical trick that you can look at in the previous slides when you're solving for the Lagrangian. And the second is a kernel trick. So basically, what the kernel trick is, it's essentially more math. But basically what it does is it takes, like, you can essentially think of it as like taking a large bunch of data points and simplifying them down into a smaller feature set, which can then be fed into an equation. So what do I mean by that? Well, ignore the math on this page, but just read the sort of bottom line. So if you apply a function to a pair of input data, you'll essentially get an output that is singular. So you can basically feed in a large amount, like maybe like 5 to 10 features in a single data point, and the kernel function, which would be sort of a pre-processing step into the SVM, would take that data, and it basically would evaluate dot products of that data in order to create or map those values into a corresponding feature space of higher dimension. So this again is a transformation, and there's a lot of math involved here, but I'm going to skip it. And yeah, so lastly, I just want to quickly end off with this idea that you essentially have to choose the kernel function, which essentially is this sort of function that condenses the data and feeds it in to whatever dimension you want it to be. And you basically have to sort of pick, when you're defining an SVM, what type of kernel you want to sort of initialize it with. And generally what I like to do when I work with SVMs is I like to look at what sort of problem I'm working on and look for what sort of solutions have been used in the past for similar problems, and then use a sort of similar setup of an SVM, right? Because generally, I'll admit my math abilities aren't obviously up to par with a lot of the stuff involved here. So I like to simplify things down for myself, and therefore I just look into what works generally in practice and what do like these papers that focus on the math conclude when it comes to the application of SVMs to real data. So you can obviously look into literature and look in a few other places to figure out what sort of kernel function works the best. But generally, what I like to do is look at the task I'm working with and see what sort of kernels have been used with similar SVMs to solve similar problems. So yeah, um, yeah. So I'll quickly. I guess this PowerPoint also sort of goes over some weaknesses and some strengths of SVMs. So weaknesses: the training and testing are slower compared to like a neural network, which is deep learning, and the advantage though sometimes is the performance of SVMs can actually be better than that of deep learning, especially when you're working with smaller amounts of data. And essentially, SVMs function the best as a binary classifier, but there are new tricks to sort of extend it past a single binary classifier to a multi-class classifier. Like I said, it's very, very sensitive to noise or bias. So therefore, if the training set has a lot of outliers or has even a few outliers, it might throw off the entire algorithm, and you might have poor performance in the testing set. And like I said, the biggest drawback is the choice. You have to make the choice of the kernel function, and there still is no like clear like path or clear choice to make when choosing a kernel function. And you sort of have to either use a combination of your intuition plus some math if you're good at that, or just look at use what other people have been using in the past and worked, and it's for work. And if it's worked well for them, then you might try applying a similar kernel to your problem. And some strengths. Training is easy. You don't have to deal with local minimum, which I'm going to explain more when we talk about gradient descent in a few weeks. And the SVM solution is always unique, which is actually really important because that allows for solutions to be reproducible when using SVMs. Additionally, it doesn't suffer from the curse of dimensionality. Essentially, what this means is generally, when you're working in machine learning, you always want to simplify the problem, right? As soon as you start adding in more features, more variables, the problem always gets more complicated. But the good thing is SVMs are actually more resilient when it comes to that, and you can actually add more features or variables to see the performance. You don't have to perform as much like pre-processing and feature engineering, and your results won't actually be that much worse. It's also less prone to overfitting, which we talked about briefly, which is sort of when the algorithm focuses too heavily on what the training data says and therefore performs poorly on the testing data. So when someone says that the algorithms overfit, that means it's sort of too focused on what data points or what data was found in the training set. And yeah, that's kind of all I wanted to talk about with SVMs and sort of a lecture format. So now we'll actually look at like the implementation of these, and this next section will be a lot easier to understand. So here, I try to make sure that nobody is like super confused. It's more important to just understand the general idea right now. I don't expect you to understand the specifics. So does anyone have any questions? No questions. Okay, cool. So now we'll move to the implementation stage. So here we took two problems that are pretty important and pretty practical, and we created some pretty practical solutions to them. So these two notebooks were taken from online, so these were not created by us. So there's a few things that we'll skip over, but I'll just kind of explain a lot of the stuff while going through it. So give me a second to pull this up, and then we'll get started. So first we'll start off with this sort of breast cancer classification problem. So any sort of binary diagnosis is often very good. SVMs are actually very good at that generally, because like we talked about with the example that we saw at the beginning of the SVM PowerPoint, when you sort of only have two classes, it's oftentimes really easy to put or create a decision boundary between those classes, even if you have high dimensions, just because SVM specialize at that. And yeah, so let me quickly share my screen, and then we'll quickly take a deeper look into this. So breast cancer is a big cancer, affects a lot of women, and machine learning can detect this cancer up to pretty high accuracy. So up to 97%, while physicians are only at 80%. So this is an example of machine learning performing better than physicians in a clinical setting. So here, this project was done by some guy on GitHub. I don't know why he did this project, but I think maybe it's just for him to get a better understanding of the disease and of sort of what clinical variables are involved. But basically, what sort of variables we're working with? We're working with ID number, whether their tumor is classified as malignant or benign. If you guys don't know what those terms mean, a benign tumor means that it's not metastatic or not cancerous, which means that it won't spread. So it's sort of a more harmless tumor. So therefore, the survival rate and the prognosis is a lot better. But if you have a malignant tumor, it's usually generally worse because you have a metastatic cancer, which means the cancer can spread from the breast to other areas. And therefore, you need to get it evaluated quickly. So it's important to sort of have an accurate screening mechanism to figure out whether people have malignant or benign tumors, and to do so with the high accuracy. So these are the sort of attribute informations we have. And then we have 10 feature values, right? So first we have the radius of the tumor. We have the texture of the tumor. So the radius is defined as the mean of the distances from the center to the points on the perimeter of the tumor. The texture is the standard deviation of the grayscale values. So they basically took likely some sort of scan of the breast cancer. So maybe just took a scan of that, and then they took the image, the resulting image, normalized it, and then took the standard deviation of those grayscale values in that image. Then they calculated the perimeter of the tumor, the area of the tumor, the smoothness of the tumor, which is considered or calculated as the variation in radius lengths between the different points. So something has small variations, so it's basically perfectly circular. It'll be very smooth or considered very smooth. Compactness, which is defined as the perimeter squared over the area minus 1. The concavity and the concave points, which is basically like how kind of sloping the tumor is, or like the surface of the tumor is. This next is the symmetry, and lastly is this sort of fractal dimension, which I'm not quite sure what it is, but I'm sure it has some sort of clinical meaning. So the first thing we do is they take the data from this online data source, and they kind of load it in. So we'll do that too. And then, so here is basically what we loaded. We loaded this sort of data set, entire data set, and now we kind of want to put it into a nice data frame that we can look at, right? So let's put it into a nice data frame. So here we see the first 5 kind of patients or 5 entries, and we basically get a lot of these clinical variables and their values for each patient, and we can see that the data is organized well. So now let's explore our data set further. So first, let's quickly look at the shape, which gives us a number of rows and columns that we talked about. Then look at the columns that we have and make sure that the names match up to what we see. They do, so that's cool. Now let's actually do some sort of basic visualization of what we have. So first thing we always want to do, this is very important. When you're working with classification algorithms, you always want to make sure you have a balanced data set. Wait, so what I mean by that is when you start off with maybe like a problem where you're trying to figure out whether, I don't know, you can automatically classify whether people like ice cream or not, right? So it's a pretty trivial problem, but let's say you want to figure out whether people like ice cream or not, and you want to do that based off of a set of variables, and you have 450 people that say yes to the ice cream, that they like ice cream, and 550 people that say they don't like ice cream, and you have a bunch of variables to that kind of help you figure out whether they like ice cream or not, which is why you're running a machine learning algorithm. So in that case, it's fine because the data set is pretty balanced. It's about 50% people who like ice cream, 50% that don't. But once you get to a point where you have a lot more people that don't than do, which is very common for sort of medical problems when you sort of have a data set of people that have a disease and don't, because generally most people for most diseases don't have the disease, right? Just because the US is a pretty healthy population. So for most diseases, you'll be lucky to have 5% of the data set have people that have the disease. So therefore, to perform some techniques called data augmentation, so that's sort of the class of techniques where you basically augment the amount of data you have in a specific class. And this can be done by duplicating patient data. It can be used by done by transforming existing data you have to create synthetic data to add. It can also be done by what's called downsampling of the dominant or the majority data set or the majority class. Sorry. So you can basically select sort of entries, a percent of the entries from the larger, the more dominant class, and use those only for the training. So there's a lot of different options here, but I just want to make sure that you guys understand that you want to give your machine learning algorithm the most unbiased data, which means that you want to give it almost equal amounts of the classes you're working with, and you also want to give it data that's similar to what it'll see in the testing set, because otherwise it won't perform well. So let's go back to this. So we run this and we see that we have 212 malignant people and 357 benign, which is like sort of a little bit imbalanced, but overall it's balanced enough that we don't have to kind of do some extra steps. So next thing we do, which is also important, but it depends on the context. So when you're working with data or variables that you don't fully understand, so for example, if you're looking at a very specific medical problem, for example, right? Sometimes some variables that you might be collecting may not be completely known to be associated with other variables, right? Because in medicine in general and with health, there's a lot of times a lot of diseases that actually are related to each other or can sort of aggravate another disease, and they haven't been well studied. So people don't really know the relationship between diseases or between a certain risk factor in a disease. So you oftentimes can use a objective numerical approach to see whether there's a correlation. So you can basically literally plot all your variables against themselves, which you'll see will happen here once this finishes loading. So essentially, we basically plot every variable against itself, which is why if you look down the diagonal, it's perfectly 1, right? Because each variable is 100% correlated with itself. So if you look through here, you'll see that some variables have a pretty high and significant correlation, right? So you have like 0.71 between the perimeter error and the mean concave points. So when you start to see high correlations, if you're especially working on a research project, for example, or something where it's important to make sure that your algorithm takes account for all these biases, you might want to exclude or remove some of the features from further analysis, right? And this is something I also wanted to bring up just so you guys are aware of. So yeah, we run this, check the correlation, and some of them are high, but for the purposes of this project, we won't worry too much about them. So like you said, there's strong correlation between the mean radius, the mean perimeter, the mean area, and the mean perimeter, which makes sense, right? Because generally when you're working with tumors, you'll actually see that the radius and perimeter of the data generally have high correlation. So now we will begin training the data. So first thing we do is we drop the specific kind of dependent variable, which is whether it's benign or malignant, and we keep all the other columns, and then we make the y kind of, or the independent variable, the dependent variable, whether they have a malignant tumor or not, where 0 represents malignant and 1 represents benign. So now we'll use this sort of handy-dandy library that we talked about before to split the data. Remember that splitting the data is very important, and the distribution you decide to use is also important. Generally, 70-30 is commonly what's used, 70% for training, 30% for testing, but you can use 80%, 20%, and you could possibly even use 90% for training and 10% for testing if you have a really large data set. So that's like more than 3,000 or 4,000 entries or rows, you can likely get away with doing 90% and 10%. But anyway, so let's quickly check the sizes of our training and testing data. So the sizes make sense. We have 455 different patients in total in our training set, and we have 30 different columns or features. And the testing is 114 patients, and obviously the columns shouldn't change, and the Y is the same. So now let's basically import the support vector machine model. So this is the kind of library we import it from, and then you basically define it. And now let's fit it to our training data set. So yeah. So basically, when you don't specify a kernel, it automatically chooses one for you. So generally, you don't always have to specify one. The RBF, by the way, stands for the radial basis function kernel, and it's one of the most popular kernels that's used with SVMs. But if you're curious on what specifically it uses or what sort of transformation it performs in the data, you can kind of look at it in your own time. But generally, wait, I don't know why this was updated. But anyway, yeah, so the rest of it's sort of this pre-done settings. So we're not going to mess with them right now. Just going to see how the base SVM with no sort of parameter specifications works. So now we trained it, we fit it to the data, and then we predict from the testing data and figure out what predictions our model gives. So now we can generate what's called a confusion matrix. So what a confusion matrix is, it basically shows you these four things. It shows you true negatives, false negatives, and true positives. So a true positive is a positive class observation that is correctly classified as positive by the model. A false positive is a negative class observation, which is 0, which is incorrectly classified as positive by the model. A true negative is a negative class observation that is correctly classified as negative, and a false negative is a positive class observation that is incorrectly classified as negative. So generally, confusion matrices are pretty popular when working with data in a tabular format or like in a data frame, just because it's generally a good representation of what we can see. So here we make the confusion matrix, and we see that we're actually doing pretty good, right? Only 8 samples have been correct, misidentified, right? So out of the whatever 114, 8 of them were incorrect, right? So we have no people that we predicted falsely, right? So we had 0 false positives, and then we had some false negatives. But generally, having false positives is generally a bigger problem, especially with screening tests, or sorry, like secondary screening tests. So it's not basically this algorithm isn't doing too bad. So we can print out a full classification report to sort of figure out the precision, the accuracy, whatever. And we can see that overall the accuracy is decent. It's 0.93, which is very good for just using a base SVM. So we didn't specify any parameters, just a base SVM. And one thing I also want to point out is like we spent like 20 minutes talking about like these different all this different computation that happens, right? But in practical implementation of these algorithms, it's literally just one line of code, which is sort of interesting when you think of machine learning, which is why you can actually do a lot of stuff with machine learning in less than like 100 and 200 lines of code. So yeah, so now let's look at how we can improve our model, right? So 93 is okay, but we can improve it. So first thing we want to do is normalize our data, right? So we've talked about how in pre-processing you can always normalize your data to increase the prediction capacity. And basically what normalization does is it brings all the values into a specified range. right? So this allows the algorithm to actually classify better because all the data from all the different variables that we have are sort of in the same range. So if we run these cells, we can see that now all the values that we have are normalized between 0 and 1. So let's normalize the rest of the training data, and let's fit a new SVM to the same data. And then let's regenerate the same confusion matrix. And here we're doing a lot better. We're all the way up to 96%. So we only have 5 false predictions now, right? So before we had like 8, so now we're down to 5. So we're slowly increasing the model, and we're up to 96%, which is pretty good. So essentially now we can improve the hyperparameters a little bit more, which I'll talk about in a second. But essentially we've basically completed our model, right? We've gotten to a point where we have the model at a good place, and we've seen how the SVM can produce a good model accuracy on a typical binary classification problem. So quickly before we move on to our second example, which is sort of more comprehensive, it allows you to look at exactly how the SVM is working, not just like how we can use it. I quickly want to talk about what grid search is. So when you're working with machine learning models, right? When we defined the model in the first place, right? We defined the SVM. There were a bunch of sort of auto parameters that were filled in just because we didn't specify values for them, or the default parameters. And generally, you always want to start off without specifying any of them. And then once you get a good understanding of the problem, you could then go in and start specifying different values for these and change them as needed. So what you can generally do is, for these different values, you can run what's called a grid search. Basically, this is sort of an algorithm that allows you to try all the different combinations of hyperparameters, right? So in this case, we're trying 0.1, 1, 10, 100. And then for C, which is basically sort of error mitigation variable is how I think of it. It's like sort of this variable that's in place to decrease the error of the algorithm. Gamma, which is just another variable, and then kernel, we can specify different kernels if we want. So essentially what this does is it counts the number of like different variables or different values for the variable to specify. So here there are 4, here there's 4, and here's just 1. So overall, when you run this grid search, it'll run 16 iterations of these hyperparameters, right? So if you go here, we start running it, right? It'll take about 16. It'll run through 16 searches to figure out which produces the best score, right? So if you look through here, it runs through all of them, and we can see that the best one was this one up here, I think, where it produced a score of 0.989, and it used C equals 100, gamma equals 1, kernel equals RBF. So this is probably the optimal parameter combination, right? So therefore, we refit the model to predict the testing set, and after we do that, we replot the confusion matrix and we're down to 3 incorrect predictions and an accuracy rate of 97%. So we've gone all the way from 92% to 97%, which is a few small changes. So yeah, so sort of in this example, we looked at how we can practically implement SVM, what the code for it looks like, and how we can do all of this in Python. And again, just want to make sure if you guys aren't familiar with all these functions, don't worry. The documentation for these different libraries is always available, and you don't need to memorize all of these functions. You can always just Google like what function allows you to create a confusion matrix, and you can just Google that, and it'll give you like the code for that. So you oftentimes don't have to like manually go through and do a lot of this stuff. But anyway, we'll upload both these notebooks for you guys to go play around with and like look into. Because again, I'm doing this without you guys kind of interacting with it right now. So once we finish, we'll upload these and you can take a look at them. So yeah, we're done with this notebook. So let's extend. So now let's actually produce a visual representation of SVMs in Python. So first thing we're going to do is we're going to import a bunch of libraries that will help us with plotting. So we got this, but we're going to load it. And we quickly are going to create some random data, right? So we take this sample generator and make a bunch of random blobs, right? So so we create these random blobs right here. And now we're going to look at what a linear discriminative classifier would try to do, which is basically just a fancy way of saying what would happen if we try to just randomly draw lines across these different points, right? To sort of divide these into two separate classes. So if you do that, we end up with these lines that all do technically separate the data, but in actuality are quite different from each other, right? Because when you look at the testing data set, we'll likely see very different distribution. So like we talked about, the goal is to maximize the margin between the different classes, right? So let's choose between these different three lines and see which maximizes the margin, right? So we're going to draw an equidistant margin across. Equidistant just means same distance on both sides of the line from each of these different points and see which maximizes the margin. Right. So if we draw this, we can see that the line in the middle, the one in between the twos on the outside, is likely going to be the most accurate because the margin doesn't overlap any of the points, right? If you look at the top one, the top of the margin overlaps this class, and on this one, the bottom of the margin overlaps the yellow class. So in support vector machines, the line that maximizes this margin is the one we will choose as the optimal model. So here we're basically going to do the same thing with the X and Y data that we have, but this time we're going to use the linear kernel from the SVM and see what sort of line it produces. So we're going to use scikit-learn like we did last time on the other example that I showed you. And let's quickly visualize how this looks, right? So we're basically going to plot what the decision function looks like. So this is the line it gave us, and this is sort of the margin that it created, right? So you see the margin sort of overlapping the point, but it produces a line of maximum estimation that increases the margin to the maximum possible amount. So again, notice that just a few of the training points are touching the margin itself, and these different points are known as support vectors, as we talked about in the PowerPoint, and you can figure out kind of their point values by looking at this attribute called support vectors. And currently, they're two-dimensional, right? Because we're working with two features. But once you start to get to high dimensions, we get to n dimensions, we'll have n dimensional support vectors. So yeah, now let's do the same thing, but let's see what happens if you plot a model, learn from the first 60 points and then the first 120 points of the data set. So here, we are basically just going to plot two different plots. In case you're wondering, zip just means we're gonna kind of try both 60 and 120 with the axes. So we're gonna plot either 60 or 120 points. And once we do that, we're going to see the difference in the predictions. So as you can see, when we have more data points, the margin is actually going to the margin itself, or the sort of points that are chosen to be the support vectors, actually do not change. So this sort of insensitivity to the behavior of the points is one of the strengths of the SVM model, which is why when you sort of have smaller amounts of data, SVMs outperform like more complex models like neural networks, which we'll talk about. And you can also run this interactively, but we're not going to use that right now because you're not using IPython. And here, I don't see there's anything else I quickly want to talk about. So I don't think there's anything else here that's super important. If you want, you can run some of the higher dimensional visualizations to kind of see how the decision boundary points look, and to see how the functions can be visualized as. But yeah, here they actually show you how the kernel trick can be done with these points. So there's, of course, there's still math involved here. But if you want, you can go back and look at it on your free time to see how the transformation was applied to create the model from. So this is a 2D representation of the data that's seen up here. So you can kind of look through the code and figure out how they transform data from 2D to 3D. But I'm not going to go over that right now. It's not super important. So yeah, let's look at a different example now. So before we looked at breast cancer, right, which is sort of this thing that can easily be written as numerical, right? We can transform the diagnosis to zeros and ones because it's a binary diagnosis. But with faces, we have a completely different scenario than what we saw with a bunch of very clinical variables that are given objective numerical points or scores. So here we're going to use a bunch of faces and try to use an SVM to sort of classify these different people. So first thing we're going to do is we're going to download this data set, which might take a second apparently. So just going to skip that for now, and let's look over here. So here we see that the data that we're given gives the image of the person along with their name, right? And each image contains 62 by 47 pixels, which means that the total number of pixels in each image is around 3,000. So the simplest, like kind of naive solution to this problem is just to treat each pixel value as a different feature, right? But this is actually not going to be very effective because you have too many features now. 3,000 features, even with an SVM, is still too many. So we use this sort of dimensionality reduction algorithm, which is essentially a fancy way of saying we're just removing features that are unimportant. And they use something called PCA, which we'll talk about more. But essentially, PCA just tries to minimize or tries to remove all the features that are of high bias or high variability throughout the data set. So between the different images, which pixels have a lot of have a high standard deviation or high bias, and so we basically just extract 150 components from the 3,000 pixels. So one thing I want to clarify is with PCA, something that can be done is you can take these 3,000 pixels, and then instead of just removing 2,850 of them and just keeping 150 of them, you can sort of condense the data into 150 components. So these 150 components essentially contain the same information as the 3,000 pixels, but it's just a condensed form of it. It's not like you're selecting only 150 pixels. So yeah, we run a randomized PCA, and then we create the algorithm, or the support vector machine algorithm. Did I not import? Well, I guess the class randomized. Do we have this? I don't even know. Okay, I'm just gonna skip this for now because I'm not. This is some sort of importing error, which you guys can look into yourselves. I don't know why this is not working. Maybe the package isn't called randomized PCA. Maybe it's called something else. But let's not worry about that now. So the theory is what's more important. So we create the SVM, right? We use the general kernel, which is the radial basis function, or RBF. We set this parameter called class weight, which is essentially what I was talking about earlier, which is where you want to make sure that your classes that you have, in this case, you're working with many classes, right? You're not just working with binary classifier. You're working with like I don't know, multi-class, right? Because each of these people is a different person, right? So here we're looking at like 5 or 6 people, right? So it's probably 5 or 6 classes. So setting this class weight equals balanced means that the SVM itself will take into account that the class that the weighted will take into account the weightage of the different classes in the training set, which is sort of good for us because it'll understand that there's some bias and it'll sort of account for a little bit of it. And then we'll run some cross-validation, which is essentially just a fancy way of saying we're going to test some of we're going to test the algorithm on some of the data from the training set without kind of looking at data from the testing set to have some sort of metric. And then we use grid search, which we looked at in the previous thing, which basically just allows you to try different hyperparameters. And then we figure out the best set of hyperparameters, which may be these. Apparently, so it's 0.001 for SVC gamma, and then for the C, or the sort of error mitigation variable, the optimal value is 10. And now we can finally just predict the model by selecting the best estimator model from the grid search, and then predicting the values it gives us. And overall, we actually see that we're predicting most of these really well, right? We only miss the one down here, where instead of predicting George W. Bush, I think is that George W. Bush? I think, or is that HW? I don't know. It predicts Tony Blair, which is some guy from the UK, I think. Yeah, so we only have one incorrectly classified sample, which is overall pretty good, and our accuracy overall is still very good throughout. And lastly, we can make a simple confusion matrix and show that overall we're only classifying around or misclassifying around like 15 to 20 of these images when we have like a lot of images. We have over probably about 250 images. So overall, even with the very, very simplistic SVM, which is literally just taking a smaller subset of features from smaller subset of features from the pixels that we started off in each of our images, we still are able to end up with an SVM that classifies really well. All right, so I've been talking a lot today, and I want to make sure that everyone leaves to today's sort of, I guess you can call it lecture, or today's subclub meeting with a really good understanding of SVMs and how they work. So again, you don't have to know all the details, but just the big picture ideas. So I'll give you guys the last like 4 to 5 minutes today just to like ask any questions. Do you guys have any specific things you guys would like to talk about or mention? Okay, no questions. If you guys don't have any questions about today, you can even just talk about like what I don't know, how your spring break, winter break was, not spring break, winter break, how your winter break was, if you want. Just any questions you guys have or anything you guys want to say.